So dear students, let us learn more about the electric charges and the fields. And in the last class, we have discussed many equations related to electric field and electric potential. If we take a system of two charges, Q1 and Q2, separated by distance r, we can measure net electric field between these two charges, or you can even find the field outside the line joining the two charges. We can find net field anywhere around the charges. And when we find net electric field, if we get zero electric field, then such point is called electric neutral point. So, where do we get such electric neutral point? When we consider system of two charges Q1 and Q2. If the charges are like charges and if they are of equal magnitude, that is Q1 plus Q2, and if they are of equal magnitude, then the position of the null point will be the position like and equal. The position of the null point will be exactly midway between the two charges. Midway between the two charges. That means we get exactly at a midpoint, because at the midpoint the field due to plus Q1 and the field due to plus Q2 are equal and in opposite direction. That is, due to this plus, it will be away from it. Due to this positive, it will be again away from that charge, and they get cancel each other, giving zero electric field. So, if the charges are like charges, equal magnitude, the null point lies exactly midway between the two charges. If they are like charges and if they are of unequal magnitude, then the null point lies between the two charges, nearer to the weaker charge. It lies between the two charges, nearer to the weaker charge. Let me consider that Q1 is a weaker charge. So let us assume that Q1 is lesser than Q2. Then it lies nearer to the weaker charge at a distance x, so that the remaining distance is r minus x. So it lies between the two charges, nearer to the weaker charge, As I've assumed that Q1 is lesser than Q2, so that's why it lies nearer Q1. If Q2 is a weaker charge, then it lies nearer Q2. And we can find this value of x. By equating the two fields, we can find this value of x to be equal to r by square root of Q2 by Q1 plus 1. So that is the shortcut formula used to find the position of the null point between the two charges nearer to the weaker charge. Now, what if the charges are unlike charges and if they are of equal magnitude? If the charges are unlike charges and if they are of equal magnitude, then there will not be any point. So, no null point is possible in this case. The reason, because between the two charges, if we try to find the position of the null point, the two fields will get added up. So, that's why there is no null point. If the charges are unlike charges and unequal magnitude, then the point lies outside the two charges, outside. Null point will be outside two charges, nearer to the weaker charge. So in this diagram, it will be somewhere here because Q1 is lesser than Q2, and if Q2 is lesser than Q1, it will lie on the right hand side of Q2. So we can find that again from Q1, let it be x, and that x can be calculated using similar format of the equation, which is x is equal to r by square root of Q2 by Q1 minus 1. So this is the method of finding null points. So what is a null point? It's a point in an electric field where the resultant electric field is 0. And what is the force experienced by a charge placed at that point? So force experienced by a charge placed at that point is 0 because the force is always given by charge placed into the electric field. Electric field is 0. So force is also 0 at such point. Just the way we have found the point of 0 electric field, it is possible to find the position of point or points of 0 potential. If I take two like charges of equal or unequal magnitude, and now if you try to find the point of 0 potential, we don't get anywhere around the charges or on the line because potential due to the positive charge and the potential due to the other positive charge, they'll get added up, so we cannot be 0. So which means point of 0 potential is possible only between two unlike charges, not between two like charges. So if I consider two unlike charges, Q1 and Q2, separated by a distance r. So if the charges are unlike charges and are of equal magnitude, then this is the point anywhere on this line, okay. So we get that is midway between the two charges. So midway between the two charges, net potential is 0. Not only here, at any point on this line it is 0 because these points are at equidistance from both the charges, and this particular line is called as equipotential line. It's called equipotential line. So unlike charges and equal magnitude, we get point of 0 potential exactly midway between the two charges. And if the charges are again unlike, and if they are of unequal magnitude, there are two possibilities where we can get points of 0 potential. One point is between the two charges, and nearer to the weaker charge. And we can find that somewhere in between, assuming the same, that's Q1 is lesser than Q2, and if the point lies somewhere here, then that x is given by r divided by Q2 by Q1 plus 1. So that is x, which you can find where it lies in between the two charges nearer to the weaker charge. One is positive, other is negative. And in the same case, we can even get a point of 0 potential outside the line joining the two charges. The other point is outside the line joining two charges and nearer to the weaker charge, That is x is equal to r divided by Q2 by Q1 minus 1. So that is the formula which is used to find the points of 0 potential. So let me write that here. So that is x is equal to q2 by q1. q2 by q1 minus 1 is the formula used to find the points of zero potential outside as well as inside the line joining the two charges. In the case of like charges, there is no points of zero potential. So these two concepts are important, that is finding null point and finding points of zero potential. So if there is a source charge which produces electric field, in that charge, if I place another test charge, so this is the source of electric field, and if I place another test charge Q0, then this charge not only experiences force, which is given by F is equal to Q0 into E, but in this charge, it possesses or it stores the energy in it. What kind of energy? What form of energy? Electric potential energy. And we can find that potential energy U is equal to charge into potential at that point. So if you want to find the force on it, multiply that charge by electric field at that point. And if you want to find the energy stored in it, then multiply that charge by the potential at that point. So this is the formula for energy stored in a charge in an electric field. But if I take system of two charges, Q1 and Q2, separated by a distance r, then what is the energy stored in the system? This is the energy stored in one single charge at a particular point. What is the energy stored in the system? The energy stored in the system is given by U is equal to 1 by 4 pi epsilon naught Q1 into Q2 by R. So this is the energy stored in the system of two charges. And using this energy, we can even find the force. Force is always equal to negative potential energy gradient. F is equal to minus du by dr. So if you differentiate this equation, du by dr, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, Q1 into Q2 by R. Q1, Q2 is a constant. So differentiating U with respect to R, differentiation of 1 by x is minus 1 by x square. Differentiation of 1 by R is minus 1 by R square. So minus 1 by 4 pi epsilon naught Q1 into Q2 by R square is nothing but minus F. Because this is the equation that we get from the Coulomb's inverse square law. So we have proved that du by dr is equal to minus F. So force is always a measure of negative potential energy gradient. And if it is a like charge, if R increases, then U decreases. If R increases, U decreases, and F is repulsive. If R increases, U decreases. That's only in the case of like charges. If it is unlike charges, if R increases, then U also increases. If R increases, U also increases, then the force is attractive. If R increases, U also increases, then F, and again in this case, see, if R increases and if U decreases, then F becomes positive. F is positive. So positive means it's repulsive in nature. And if R increases, U also increases, then F is negative. Your F is negative. And when F is negative, the force is always attractive in nature. So this is the energy stored in a charge at a particular point. This is the energy stored in the system of two charges. If there is a three charge system, Q1, Q2 and Q3, separated by R12, R23 and R31, then the energy stored in the system of three charges is given by U is equal to 1 by 4 pi epsilon naught Q1, Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R31. So this is the formula for energy stored in the system of 3 charges. The energy stored in the system of 2 charges, this is in the system of 3 charges. Where the way to remember is that between 3 charges, how many one-to-one relations are possible? So that many number of terms you need to write. Between 3 charges, there are 3 one-to-one relation possible. That's why we get Q1, Q2, Q2, Q3, Q3, Q1. Between 2 charges, only one such one-to-one relation possible. That's why we get only 1 term. So depending on one-to-one relation, we can write that many number of terms to find the total energy stored in the system of charges. Capacity of a conductor is its ability to store electric charges, and it's defined as the ratio of charge to the potential difference. And capacity is independent of the charge stored on the conductor. Its SI unit is farad, denoted by capital letter F. Capacity of a spherical conductor is given by 4 pi epsilon naught into R. Now that is when surrounded by air, and C is equal to 4 pi epsilon naught epsilon R into R when surrounded by a dielectric medium having dielectric constant epsilon R. Now when n identical charge drops, when n identical charge drops are combined to form a larger drop, then the charge on the larger drop is equal to n times the charge on the smaller drop. Radius of the larger drop is cube root of n times the radius of the smaller drop. Surface density of the larger drop is cube root of n times the surface density of the smaller drop. Capacity of the larger drop is equal to cube root of n times capacity of the smaller drop. Potential on the larger drop is n to the power 2/3 times potential of the smaller drop, and the energy stored in the larger drop is n to the power 5/3 times energy stored in the smaller drop. So these are the equations related to an identical drops, charge drops. When combined, what is the relation between the various physical quantities that we get from this particular table? So this is the charge, radius, surface density of charge, capacity, potential, and the energy stored in the smaller drop. An arrangement which is used to store charge as well as energy is called capacitor. So in capacitor we have 2 identical oppositely charged parallel plates, oppositely charged parallel plate having charge plus q and minus q, and separated by a distance d. So what is the, and having A as area of the plate. So what is the surface density of the charge on each plate, which is charge per unit area, Q by A. And we assume that these plates are very close to each other, so that electric field due to each plate, electric field due to each is given by sigma by 2 epsilon naught, which is a sigma is Q by A, so it's a Q by 2 A epsilon naught. Then what is the net electric field in between? This is the electric field produced by each plate. So what is the net electric field between the plates? It is sigma by epsilon naught, which is Q by A epsilon naught. And because of this field, a potential difference is created between the plates, which is given by V is equal to E into D. And E is here, which is Q by A epsilon naught. So therefore, we'll get Q D by A epsilon naught. And based on this, we can find the capacity is equal to A epsilon naught by D. That's in air, with air as the dielectric in between, and C suffix Cl, right? And then Cm, which is in a medium, we get A is equal, C is equal to A epsilon naught epsilon R by D. So that's in a medium. So that the ratio of these capacities, Cm by Ca, will give you the value of epsilon R, which is dielectric constant, is the ratio of capacity of the capacitor in a medium to the capacity of the same capacitor with air as dielectric. And once it is charged, if there is a dielectric, we can store energy between the plates, and that energy stored, U, is given by half Cv square, half Q square by C, half QV. So that is the energy stored in the capacitor. We can find energy per unit volume, which is energy density. It's called energy density. So energy density is U is equal to half epsilon naught E square. So that's the energy per unit volume. Now energy density is equivalent of energy density, which is energy per unit volume, is equivalent of the pressure. So these two plates, they exert force normally, and normal force per unit area is called as the pressure. So therefore, the formula for pressure P is also equal to half epsilon naught E square. So because energy density and pressure, they have the same dimensional formula, therefore their magnitudes are definitely same. So pressure is force per unit area. Therefore, what is the force acting on each plate? So force is equal to half A epsilon naught E square. So that is the force of attraction between oppositely charged parallel plates. Now based on this equation, U is equal to half Cv square or U is equal to Q square by C, the kind of the graph that we get is, so that's U versus Q or U versus V. U versus Q from here, U is equal to half Q square by C, and from here U is equal to half Cv square, and both the equations are of the form y is equal to a x square. So that's why you will get a parabola symmetric about the y-axis. Similarly, even here the equation regarding energy density U versus E is again of the same format, which is y is equal to x square. So again you will get a parabola. If I draw Q versus V, Q is equal to Cv. This equation is of the format y is equal to mx. So it is a straight line passing through the origin, and the slope of it gives a C, that is the capacitance. And then if I measure the area below the graph here, so area is, it's a triangle, half into base into height, which is half QV. So area is half QV, and that gives the energy stored in the capacitor. So these set of equations are very important, using which any quantity related to a parallel plate capacitor can be very easily calculated. The next important topic is a combination of the capacitor. So there are basically two combinations. One is a series combination of the capacitor, and the other is a parallel combination of capacitor. In series combination of capacitor, charge is same on each capacitor, whereas in parallel combination, potential difference across potential difference across each capacitor is same. And in series combination, potential difference across the combination is equal to sum of the potential difference across each capacitor, whereas in parallel combination, the total charge stored in the combination is equal to sum of the charges on each capacitor. Effective capacity 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and here we get Cp is equal to C1 plus C2 plus C3. For two capacitor, Cs is equal to C1 C2 by C1 plus C2, and here for two capacitor, Cp is equal to C1 plus C2. When there are n identical capacitors, Cs is equal to C by n, and in Cp here is equal to n into C. The ratio of the potential difference V1 is to V2 is to V3 is equal to 1 by C1 is to 1 by C2 is to 1 by C3, and here the ratio of the charge Q1, Q2, Q3 is equal to C1 is to C2 is to C3. The energy stored in the combination Us is equal to half CSV square, whereas here the energy stored in the combination UP is equal to half CP V square. So these equations based on the combinations are again important. There are a lot of numericals based on the combination, maybe to find the effective capacity or to find the energy stored or even to find the charge on each capacitor. So such questions normally they ask in the examination. So now we are going to analyze one more important special case when two capacitors are connected in parallel, and the condition is that at least one out of the two, at least one must be charged. Only then all the equations that we are analyzing are useful. So what is the concept here? When two capacitors are connected in parallel, and when we connect them, we have to make sure that out of the two, at least one. If both are charged, then it's fine, but at least one must be charged. Now, what happens when two capacitors are connected in parallel? So first, let me write here which are the quantities that we are going to learn. One, it's capacity, and then the potential difference, and then the charge, and then the energy. See, before they are connected in parallel, let's write all the variables that we have used. Before they are connected in parallel, let C1 and C2 be their capacity. Let their potential difference be V1 and V2. If one is charged, its potential difference is V1. If other is uncharged, then V2 is 0. If both are charged, then V1 and V2 are their potential difference before connecting them. This is before connecting them in parallel. And now the charge before they are connected in parallel. Q1 is equal to C1 V1 and Q2 is equal to C2 V2. So what is the energy stored? U1 half C1 V1 square. What is U2? Half C2 V2 square. Now, after they are connected in parallel, what happens? When the two capacitors having different potential difference are connected in parallel, sharing of the charges takes place. Charges will flow from one capacitor to other capacitor. For what reason the charges will flow? The charges will flow till their potential becomes same. So, after they are connected in parallel, both the capacitors will attain a common potential. So, what is their capacity after they are connected in parallel? That remains the same, C1 and C2. But their potential becomes V. It's a common potential, which is given by C1V1 plus C2V2 by C1 plus C2. This is the common potential attained by the capacitors, both the capacitors, when they are connected in parallel. So now what is the new charge? So the charge will not be Q1 and Q2. It will not remain same because there is sharing of the charges takes place. So definitely both the capacitors will attain new charges, which I have taken as capital Q1, which is equal to C1V, and capital Q2 is equal to C2V. You can see their potential is same. After they are connected in parallel, they will attain the same potential, which is given by this formula. Now what about the energy? The energy is U1 dash. There will be different energy. So U1 dash is equal to half C1V square, and U2 dash will be equal to half C2V square. So this is the energy stored in both the capacitors before and after they are connected in parallel. But when during the flow of the charges from one capacitor to the other capacitor, there is a flow of charges that will result in a current, and that current generates some heat. So there will be some loss of energy takes place. So total charge before the combination and after the combination, that remains same according to the law of conservation of the charges. Even according to the law of conservation of energy, the total energy remains same before and after, but the energy stored in the capacitor is found to be lesser than that of the energy before they are connected. So what happens to the remaining energy? So remaining energy is lost or it is dissipated as heat, and that loss of energy after they are connected in parallel is given by delta U is equal to total energy before the combination, which is U1 plus U2. And that U1 plus U2 is here, half V1 square plus half C2V2 square, minus the total energy after, that's U1 dash plus U2 dash. That is the total energy after the combination, which is here, U1 dash and U2 dash. So using that, we can always find the loss of energy. To find the loss of energy, we have a easy direct equation, which is half into C1 C2 by C1 plus C2 into V1 minus V2 the whole square. So this is the formula for loss of energy due to the sharing of the charges. Loss of energy, delta is equal to half C1 C2 by C1 plus C2 into V1 minus V2 the whole square, where V1 and V2 are the potential difference to which they are charged initially. So these equations again can be used only when two capacitors are connected in parallel, and that too when one of the capacitor is charged, at least one capacitor is charged, or even both are charged. Capacitors are even made up of a number of plates called multi-plate capacitor, or is also called as a variable capacitor. In multi-plate capacitor, we find identical plates which are arranged with the equal separation between them, and even if there is a dielectric, you find the dielectric, same dielectric between every two plates. Now here we have an arrangement where the plates are arranged something like this. So what is the effective capacity between A and B? So that's what we need to calculate. To form single capacitor, we need two plates. So two plates will make one capacitor. So let us take, let C be the capacity of a single capacitor, and that C is given by A, area of the plate, permittivity of free space, divided by separation, which is same between every two plates in this diagram. So D is the separation. So in this arrangement, what is the effective capacity between A and B? Now to find the capacity between A and B, try to draw an equivalent diagram and then see what kind of combination in which these capacitors are arranged, then you can find the effective capacity more easily. And before finding the equivalent, name the plates. Okay, so let this plates be 1, 2, 3, 4. So numbers are given to each plate. You can even write the alphabets as well. Now, the plate 1 here is connected to the terminal A. So, I am going to start from here. The terminal A is here, and from A, the plate 1 is connected. And adjacent to that, there is a plate 2 which is connected to B. So, adjacent to 1, there is a plate 2 which is connected to the terminal B. But what we get to notice here is the plate 2 is shared with the 3 as well as, with the 1 as well as with 3. So, you need to draw that plate number 2 twice, because once to form a capacitor with 1, again to form a capacitor with the 3. So, you need to draw that plate number 2 once, and that 2 is connected to B. Like this. Now, adjacent to that, there is a 3 that is connected to A. So, 3 here is connected to A. Now, 3 again shared with the 2 as well as a 4. So, it forms a capacitor with 2 as well as again it forms a capacitor with 4. So, therefore, you have to draw that 3 once again. So, this is plate number 3 connected to A, and then opposite to that there is a plate number 4 which is connected to B. So, this diagram here is equivalent of this. And what kind of combination is this? So, this is a combination where 3 capacitors are connected in parallel. And I have told you, let the capacity between each 2 plates be C. Then this becomes a C, this becomes a C, this becomes a C. Therefore, C effective is C plus C plus C, that is the parallel combination, and we will get an answer as a 3C. So, this is how the plates are arranged in a variable capacitor or a multi-plate capacitor. So, I will give you one more illustration where we have more number of plates and a different kind of arrangement. So, this is plate 1, 2 here, 3 and 4 and then 5. So, now there are 5 plates arranged as shown in the diagram. So, let us number these 1, 2, 3, 4 and then 5. So, I have to rearrange them starting with 1 connected to A. It is 1 connected to A. Now, there is a plate which is a 2. It is not connected to A, neither it is connected to B, but it definitely forms a capacitor with 1 as well as a 3. And that means I have to draw that plate 2 twice. And it is not connected to A and B. That means that particular plate is isolated from A as well as B. So, this is how we arrange them. So, this is plate 2 forms a capacitor with 1, and draw that same plate once again, that is a 2, which forms a capacitor with the 3, and then that 3 is connected to B. So, which means if at all there is a plate which is isolated from A and B, you can see here, see this plate number 2. It is not connected to A, neither it is connected to B, right? So, when it is not connected to A or B, it has to be plate that helps these 2 capacitors to connect them in series. So, this is the series combination. Whenever there is a plate which is not connected, then that set of plates are in series. Now, 3 forms a capacitor with 2. 3 again forms a capacitor with 4. So, I have to draw 4 with A and 3 with B. 4 with A and 3 with B. 4 again forms a capacitor with 5, 4 and 5. So, again a 4 here and then 5. So, now you can see there are total 4 capacitors are there in this arrangement. So, what is the effective capacity? This is C, C, C and C, and let us assume that C is equal to A epsilon naught by D. So what is the effective of C and C in series? So that becomes C by 2, 0.5 C. This is C. This is also C. And now all the three are in parallel. So therefore the effective capacity, C effective is equal to C plus 0.5 C. That becomes 2.5 C is the answer. Where's C? What is C, by the way? That C is nothing but capacity between every two plates of the capacitor. So this is how the plates can be rearranged, and then we can very easily identify the combination of the capacitors, combination of dielectrics. In a capacitor, if we introduce only a single dielectric, then the effective capacity is given by C is equal to A epsilon naught epsilon r, or you can even write it as K by D. Now, what if the space is filled with more than one dielectric? So that's what this topic is all about, combination of dielectrics. So here I'm going to write two parallel plates. These are the terminals. And then now if I draw a diagram in such a way that part of the space is filled with a dielectric of thickness d1, whose value of the dielectric constant is k1. The rest of the space is filled with one more dielectric having thickness d2 and dielectric constant K2. This is series combination of the dielectric. So what is the effective capacity in such type of arrangement of the dielectric? So since it is a series combination, we can write this to be equal to CS. That's equal to A epsilon naught. So what is important here is A is same for both the dielectric. Area of the section, area of cross section is the same for both the dielectric. They differ only by thickness and the dielectric constant. So CS is given by A epsilon naught by d1 by k1 plus d2 by k2. d1 by k1 plus d2 by k2. Suppose if you leave that space as it is with the air, if k2 is only air, this space is only air, then value of k2 becomes equal to 1. So this is how we can find the effective capacity. Suppose if this d1 is equal to d2, they are identical in dimension, then effective capacity CS is equal to, we get 2 K1 K2 by K1 plus K2 into the remaining values, which is A epsilon naught by D. 2 K1 K2 by K1 plus K2 into A epsilon naught by D. So that means that this acts as, that's only if both are of the same thickness, okay, only if D1 is equal to D2. So what is the value of K effective? So K effective is given by 2 K1 K2 by K1 plus K2. Now what if there are more such dielectric? Then you need to continue this term. It's a d1 by k1 plus d2 by k2 plus d3 by k3 and so on. And here we can find K effective like this. N by K effective is equal to 1 by K1 plus 1 by K2 plus 1 by K3 and so on. So that is basically in terms of the harmonic progression. We can even arrange these dielectric in such a way that if these are the plates, so we can arrange two dielectric, one below the other. So this is one part of the dielectric having value K1. This is the other part of the dielectric having K2, and both have same thickness, but they differ by the area. So one has an area A1, the other has an area A2. Now in such case, the equivalent capacity becomes the parallel combination, which is Cp is equal to epsilon naught by D A1 K1 plus A2 K2 and so on. So this is equivalent of the series combination of the dielectric. This is equivalent of the parallel combination of the dielectric. So in this case, they have both the dielectrics have same area of cross section but different thickness. Here they have same thickness but different area of cross section. Now if A1 is equal to A2, if A1 is equal to A2, then the effective capacity will be the arithmetic mean, which is K1 plus K2 by 2 into A epsilon naught by D. So that is what we get. That is for two dielectric. So that here the K effective will be K1 plus K2 by 2. And for n such identical dielectric, so we get K effective is equal to K1 plus K2 plus K3 and so on up till Kn divided by n, where n is nothing but the number of identical, not identical dielectrics, dielectrics having identical dimension, where n is the number of dielectric having identical dimension, and K1, K2, K3 are their dielectric constant. So instead of connecting the capacitors in series and parallel, by introducing the dielectric, it behaves like, it acts like the series as well as the parallel combination of the dielectric. Suppose if few are in series and the rest are in parallel, then use this formula in finding the effective dielectric of the combination. So effect of introducing dielectric between the plates of the capacitor, between the plates of capacitor. So what is the effect of introducing the dielectric between the plates of a charged capacitor, plates of charged capacitor? So first let us consider a capacitor which is already charged, and then it's still connected to the battery, and now we introduce a dielectric here in the presence of the battery. So when we introduce a dielectric in between the battery, what happens to its capacity? Then what happens to its potential difference, and then the charge and the energy stored? See, when we introduce a dielectric, we know that the capacity is directly proportional to the dielectric constant. So definitely capacity increases. Now when the capacity increases, the capacitor is capable of storing more charges. So immediately the charges will flow from the battery to the capacitor, so that potential difference across it will remain same as that of the battery. So potential difference will remain, this will remain same, no change. So whenever a dielectric is introduced between the plates of a charge capacitor, which is still connected to the battery, the potential difference remains same, always same. Now what is the formula for the charge? Charge is Q is equal to CV. V is same. C has increased, therefore the charge also increases. It increases. So when we say capacity increases, by what factor it increases? It increases K times, because K is the dielectric, okay? So here, it K times increases. Charge again increases. By what factor it increases? It increases K. What is K? The value of the dielectric constant. If the dielectric constant is 4, charge increases 4 times. If the dielectric constant is 10, the charge increases 10 times, even the capacity also increases 10 times. So what about energy? I can use the various formats of the energy. I will use a U is equal to half CV square. Here V is same. V is same. C increases. Therefore, energy also increases by the same factor, which is K times the energy increases, because U is equal to half CV square. Here we are using U is equal to half CV square is the equation. In another case where there is a charge capacitor and we introduce the dielectric in the absence of the battery, in the absence of cell. Here, the dielectric is introduced in the presence of battery. So, in the presence of the battery, potential difference remains same and all the rest of the 3 variable increases. Whereas in the absence of the battery, when we introduced a dielectric having value K, capacity always increases. Capacity increases, because C is directly proportional to Q. Now, when the capacity increases, potential difference decreases, and there is no source to provide the charge. So that's why charge remains the same. Charge remains the same. And in the equation, C is equal to Q by V, V is equal to Q by C. When the capacity increases, the potential difference, it decreases. Again, decreases by what factor? It decreases K times. I will use the format of the energy U is equal to half Q square by C. U is equal to half Q square by C. Here Q is constant, Q remains same. C increases, therefore U has to decrease. So energy decreases. Energy decreases by again K times. So therefore, when we introduce a dielectric, in the absence of the battery, capacity increases, charge remains same, potential difference decreases, even energy decreases. So these are 2 different cases. So while solving the problem, you need to check whether the battery is still connected to the capacitor or not, because if it is connected to the capacitor, the variations are completely different from the one which we have discussed, where we introduce a dielectric in the absence of the battery. If a capacitor is connected in this manner, so one more, so we have 2 circuits, capacity of each capacitors are C. So what is the effective capacity in 2 cases? In this diagram, we need to rearrange the three capacitors to understand whether they are in series or in parallel. So this point here is A, or a node A, and these are all points of same potential till here. Even since there is no capacitor connected in this part of the branch, these are all again points of same potential. So even this is also a node A. So if you consider this point B, this is also point B, and every point here is of the same potential because there are no other capacitor you will find in that particular branch. So that's why till here it's B. And now if I have to rearrange, the first capacitor is connected between A and B. This is A and B. The second capacitor is also connected between A and B. The third capacitor is also connected between A and B. So what we get to notice here is all the three capacitors are connected between A and B. So which is nothing but equivalent of the parallel combination. So therefore we have Cp is equal to C plus C plus C, which is 3C is the answer. So therefore here the capacitors, even though they are connected or looks like they are in series, but they are not. It is basically combination of three capacitors in parallel. Now in this combination, if this is a terminal A, so this has to be the terminal B. Sorry, this is also terminal A, because common points are identical. We call it as identical points. So now if I have to rearrange, these two capacitors are connected to itself, So this is point A and this is also point A, where when a capacitor is connected to itself, this is called shorting of the capacitor. Shorting of capacitor. When a capacitor is shorted with the two terminals connected to itself, then you cannot store charges in them because they get discharged every time when the positive and negative are connected. So in such cases, you cannot store any charge when the capacitors are shorted. So therefore, these two capacitors are connected between two identical points. In this case, you will find every capacitor between two different points. And when shorted, as you cannot store any charge in them, they have no role in storing charges in the entire circuit when connected to a battery. So that's why we have to neglect capacity of such capacitor. That means we are left with only two capacitors, A and B, and you get to see them that they are connected in series and they are identical. So that's why Cs is equal to C by 2 is the answer for that particular circuit, because two identical capacitors C and C when connected in series will give you an effective capacity of C by 2. Now in the same circuit, if a capacitor is connected here, if there is one capacitor here and if there is one more capacitor here, then if this is point A, so this cannot be point A because there is a capacitor. It has to be some other point, which I'll write C. If this is B here, again this cannot be B, it has to be again some other point called D. So now if you rearrange this entire diagram, so this is point A. So from A to C, there is a capacitor. From A to C. Then there is a C to B, there is one more capacitor. C to B, there is a capacitor. Then B to D, there is one more capacitor, B to D. B to D. Then D to A, D to A, there is one more. And then between C and D, there is one more capacitor. So this is a circuit which is equivalent of Wheaton's network of resistances, similar to the Wheaton's network of resistance. And since they are identical, the point C and point D will be at same potential. Potential at C and potential at D is same. When potentials are same, there won't be any potential difference between these two. So, in this capacitor, we cannot store any charges because the potential difference across that capacitor is 0. So, when we remove this particular capacitor, now it becomes series combination of 2 capacitor here, series combination of 2 capacitor here, and series combination of these two will give you C by 2, series combination of these two will give you C by 2, and when you add these two, C by 2 and then C by 2 will give you value equal to C. So therefore, this circuit is the modified version of this particular circuit, in which there are only 3 capacitors here, and here there are 5 capacitors, so that makes it equivalent to Wheaton's network of a capacitor. So I've explained all the important points in 2 important chapters, electric charges and fields, and then electric potential and capacitor. So very important chapter for all the competitive examination, and you have to practice after going through these videos. You have to practice more and more questions, and you have to be thorough with the topic, and only then you'll be able to attempt the questions based on this topic. Thank you.